Hi everyone, welcome back. Today we're doing an AS Mechanics 1 paper. So we'll get started. So the first one is about, two projectiles being, classic question, being projected, and then looking at their motion after projection. So all of this is going to depend on two things. Firstly, the velocity at which they're projected and the acceleration that they subsequently undergo. Now, this is a gravitational question, by which I mean there's no other force involved. It's purely gravitational force acting in the y direction. So importantly, there's no acceleration in the x direction, just continues at the velocity, the x component of the velocity. So if we want to look at the motion of these things, I'm going to define a function, yp, function of time. And this is going to be the y position of the particle p, as you might guess. So the first thing to do is to think, okay, well, what is the initial y position? Well, that's just 0. So yp at 0. So this is just using the constant acceleration equations, which we can use because the acceleration is constant. It's just g. But that initial displacement is 0 because it's going from the ground. Then you add the velocity, the initial velocity of the particle times the time that's elapsed. And then you account for the acceleration or deceleration or whatever. And that's just, 1/2 at squared. In this case, a is minus g. So a is equal to minus g for both p and q. So I'm not going to give it a sub q. So this is the full equation of motion of the particle p. Now, now there's the particle q, and its motion is governed again by the initial displacement, h, and there is no initial velocity. It starts from rest, so this middle term doesn't exist, and then it also undergoes acceleration downwards. So the acceleration is minus g because it's acting downwards. So this is true at all points, and you notice that the time parameter, the sort of time things that the y position depends on, is the same for both. It's because they're released at the same instant. So t equals 0 is the same for both of these. If one was released later, then you would have to account for that, and we've seen that in other papers. But for now, this is fine. So now that we have these general equations, we can work out the answers to the question. So for this question 1, at t is equal to t ground, so that's the seconds that takes for the thing to hit the ground, then yp is equal to 0. So we have 0 is equal to initial p velocity times t ground minus 1/2 g t ground squared. And so if you rearrange this, you get that the initial velocity is 1/2 g tg, so we divided by tg here, and this gives us that tg is equal to 2.2 seconds, because we have we have the velocity, the initial velocity, and we know what g is, just 10, about 10, so we can therefore solve for tg. Okay, and we can use these equations again for the second part. They want us to find the values of h and v. So, well, we have the information from the initial question that they hit the ground at the same time. So q hits the ground at tg too. Tg as well is what I mean. So yq at tg is equal to 0, 0 displacement from the ground. And that's going to be equal to, going back to our original equation, the initial height minus 1/2 g t ground squared. And this, we have g and we have t ground, so we can therefore solve for h. And you get that h is equal to 24.2 meters. And now you want the velocity of q at that time. So vq, which is the same as the velocity of p, so vq of t ground, well, that's just going to be equal to initial velocity minus g times t ground, and then we know the initial velocity of q is 0. So this is just minus g times t ground. So this is going to be minus 22 meters per second. So the absolute value of v is 22 meters per second, but it's a minus sign because it's acting downwards. Okay, question 2. So here's a classic balancing of forces question. You see that in the first question, you need to show that the resultant of the three forces has a zero component in the x direction. So what's the net F net in the x direction? Well, we just add up them all individually. So we have, from this guy, we have 25 cosine of alpha. So that's the x component. That's this one here. That's going to be 25 cosine of alpha. And from the other one, we get the same procedure, minus 3 cosine of beta. And then this one acting vertically has no x component. It's completely in the y direction, so we don't include it. And so this is going to be equal to 25 times 0.8 minus 3 times 0.96. And if you put that into your calculator, you'll see that that is equal to 0. Okay, sorry, not 3, 30. Otherwise, that would be very different. Okay, so the second question is exactly the same thing, except you have to now work out the y direction and then talk about the resultant. So let's first work out the y direction. So that's equal to 25 sine of alpha now, plus 30 sine of beta, minus 20. So you see what's happened here? We've taken the y component, and that's plus 25 sine of alpha for this guy, plus 25 sine of beta for this guy, because the y component is pointing upwards, minus the 20 newtons pointing downwards. So you've got to keep track of the signs correctly. You don't just add them all up. You've got to make sure you give a minus sign to ones acting in the opposite direction. And if you add this up, you'll get that this is equal to 5 newtons. Now, this is now equal to F, as in the resultant force is, because there's no net force in the x direction, all of the force is acting in the y direction. So if you think of a vector, F here is equal to 0, 5. You see? So that means that the magnitude of F is equal to 5, and it's acting in the positive y direction. So I mean that seems like a little bit overworked for something that seems pretty obvious, but it's always good to think of these things as vectors and think of magnitudes and directions in case you get a question where it's not quite so simple as being completely in one direction or another. Okay, so now they remove that 20 Newton force, the one pointing downwards, and they put another force in there. And now the resultant force has the same magnitude, unchanged in magnitude, but reversed in direction. So that means that Fy net is minus 5 newtons. And again, it's if we add up I'll just redraw it. And there's some mystery force. So we have the same components from these guys. You have 25 sine of alpha plus 30 sine of beta plus this force. And we know what that is, we know what that is, we know what 5 is, and you solve this, you get that F is equal to minus 30 newtons. So that means that this force is acting like this, and so was the previous one, but this one's much stronger. And so even though the previous one was acting downwards, the net force was still upwards. Now this new force is strong enough that the net force is going to be downwards. Okay, question 3, a power question. And so these all tend to rely on you being able to do this. That you know that power is energy over time. So I'm going to use differentials here because it is a little easier. And the energy, which is the work done, is force times distance. And this is, if we take the force out because it's constant, we get F ds dt. And dsdt is just the velocity, so FV. And this is what you need to know for these power questions. So you may well just memorize P is equal to FV. That's absolutely fine. But if you need to derive it in a hurry, remember that power is basically the derivative of work differentiated with respect to time. So VB has a velocity at point B. So that's going. If I just take F, divide this equation by F, I get V is equal to. Let's write that down. V is equal to P over F. So at point B, my velocity is going to be equal to the power at B divided by the force at B. And we're told that the power at B is 1.2 times the power at A. The force at B is 0.96 times the force at A. So this is 1.2 over 0.96 times the velocity at A, because PA over FA is VA. And you can get this is equal to 35 meters per second because we're given VA. Okay, question 2. So this is a conservation of energy question. So it's gone from A and to B, and its kinetic energy has changed. And it's also done work against friction, resistance to motion or friction. So we know that the change in kinetic energy is equal to 1/2 m VB squared minus VA squared, which is, if you work it out, is 4.41 times 10 to the 7 joules. Using scientific notation here. If you're uncomfortable with that, that's worth checking up on. In AS, it doesn't come up that much, except in these power questions where you've got like really huge energies and things going on with cars and trucks moving. But it's really worth being comfortable with if you have, if you want to do these things properly, and if you have any intention of continuing in maths or science. So, but otherwise, yeah, 4.41 times 10 to the 7 joules. And the work done by the engine must be equal to the change in kinetic energy plus the work done against friction or resistance here. And so we just worked out what delta KE is. We know what the work done by friction is. We're given it. And so you'll get that this is equal to 4.64 times 10 to the 7 joules. Okay, question 4. So here we have a block sitting on a horizontal surface, and in the first case we're told that it's smooth, so that means there's no friction force. So what forces do we have acting it? We have these two that were given. We have the weight of the thing, and we have the reaction force. So now they want us to find the value of x, given that all these things are balanced. So the net force in the x direction, so that's along here. So we don't really care. Actually, I didn't even need to draw that because we're not caring about the weight of the thing yet. So we're just looking at the x direction. So we know that x cosine of 30 degrees, so that's the x component of this force here, minus 40 cosine of this angle, which if you think about this whole thing is 180, that thing's 30, that thing's 90, therefore this thing has to be 60 degrees. So 40 cosine of 60 degrees. Oops. And so if you work this out using your similar triangles, or you get this, or you can just use your calculator, these things a lot of the time. And so this must be equal to 0 because the thing isn't moving in the x direction. And if you solve, you get that x is 40 over square root 3, which is 23.1 newtons. So now they're saying, okay, well, what if the surface was instead rough, i.e. you now have to think about friction. And they tell you that the block is in limiting equilibrium. And the frictional force acting on the block has a magnitude 10 newtons. So let's have this guy. We have the 40 Newton force like that. We have, at a right angle to it, x, the x force. That's 60. And firstly, let's look at the x. Sorry, so this, where was A? Was it to the left? Yeah. So now we have a friction force acting to the left. like so. And now we need to find the coefficient of friction between the block and the surface. So firstly, let's find out what x has to be, because that's x has now changed. The thing still isn't moving, so all the x forces must still be balanced. So F net x is 0, and this is going to be equal again to x cosine of 30 minus 40 cosine of 60 minus 10 newtons, which is this extra bit acting in the sort of negative direction. And if you solve, you'll get that x is equal to 34.6. Now we're going to think about the effective weight of the block. So the weight of the block is mg, but it's kind of, the ground isn't feeling all of that because it's got these other two forces pulling up. So I mean, the reason I'm saying this is because we know that the force of friction is equal to mu times r, and r is the reaction force that the ground exerts on the block, and that exactly counters the force felt by the ground from the block. And usually, if there's no forces, like other forces on the block, it's just going to be the mass, the weight of the block, mass times g. But here we've got these other forces kind of lightening the load. So the reaction force is going to be equal to mg minus x sine of 30, which is this guy. And there's another guy is also helping to lighten the load, and that's 40 sine of 60. And this is equal to the friction force, which is equal to 10. And if you solve, we know mg, we know x sine 30, we know 40 sine of 60. And so that gives us that mu is equal to 0.102. Okay. Question 5. So we have this one of these pulley problems, and it often, a lot of the time for these is taken in just passing the question and understanding what it's asking, because they can be, you know, relatively complicated scenarios. So what we have is a system at rest that's then released, and motion begins this way. So I'm going to define this kind of motion to the right and then down as the sort of positive motion. So we know that the surface is rough. So there's going to be some friction, and the friction is going to be acting that way against the motion. There's obviously no friction on A because it's hanging freely. So firstly, we want the work done against the frictional force acting on B. So firstly, we want to find the frictional force, which again is just mu times r. And r here is just going to be the weight of B. So that's mu mbg. So that's equal to 2.1 newtons. And then we know that the work done by friction is the force of friction times the distance traveled. And we know they've given us for the distance traveled, they've asked us how much work is done during the first 0.9 meters. So that's going to be the force of friction times the distance traveled. And that's 1.89 joules. So that's pretty straightforward. Now they want the loss of potential energy of the system. Well, if you think about it, so during this first 0.9 meters, because the string is light and inextensible, it means it's always the same length during the motion until, you know, unless it breaks or something, which means that if B has moved 0.9 meters, then A has moved 0.9 meters down. Now B hasn't moved up or down, it's just moved along. So it hasn't lost any potential energy. But A has lost some potential energy because it's gone down. So delta potential energy of the whole system is just going to be mg delta h. And delta h is 0.9 meters, so this is just ma times g times 0.9, which is 2.7 joules. So therefore, what is the gain in kinetic energy? Well, we know that the change in total energy is 0, conservation of energy, and that's going to be equal to adding up all the changes that you could possibly have if you include work done. if you don't include work done in your definition of energy, this is just purely a conventional thing. Either you say energy never changes, and then you count the work done by friction as energy, which I think makes sense, because really friction, you're kind of doing work on the ground or on the surface. But some people like to say, oh, the change in energy is equal to the work done, in which case the work done would just go on the other side. But this is the way I prefer to think about it, because it's always applicable. As long as you account for all the possible forms of energy, this thing will work out and equal 0. So therefore, that means that the change in kinetic energy is going to be equal to the change in potential energy. Or minus the change in potential energy. So here's a sign convention. So actually it's lost potential energy. So the change in potential energy is actually minus 2.7 joules, because the height change was minus 0.9. So this is just being a bit fussy, but I'm going to keep it this way. I'm going to say that the increase in potential energy is negative, which means it's decreased. And then subtract the work done by friction. And so this is going to be minus 2.7 minus 1.89. And this is therefore 0.81 joules. Now the string breaks, and at this point A is at a height of 0.4 meters. And now they want us to find the speed at which A reaches the floor. So firstly, let's find the velocity when the thing breaks. Well, remember that kinetic energy is 1/2 mv squared, right? And so so this is going to be equal to 1/2 ma v break squared plus 1/2 mb v break squared. And I can only say this is true because they're going to be moving at the same velocity, because the string is kind of stiff between them before the string breaks. So they're moving as a unit. And so the velocities are going to be the same. And I know the kinetic energy, right? So I can then solve by saying that the v break, which is true for both of them, is 2 times the kinetic energy divided by ma plus mb. And just to clarify, the kinetic energy here is the same as the delta kinetic energy that we had before, because they started at rest. So the change in kinetic energy is equal to the total kinetic energy that they have. So if I solve for this, I get that this is 1.64 meters per second. And then I can use, so this is a very, very cool equation to use when you don't have time. So we don't really know anything about the time and anything is taken, and it would probably be horrendous to try and work it out. So if you want to kind of skip the time and if you get a distance instead, then you use this equation. V final squared is V initial squared plus 2 times the acceleration times the distance traveled. So that means that here our V final for A is the square root of V break squared plus 2g times 0.9. So here my acceleration is equal to g, not minus g, because I've defined going along and down as a positive direction. So it's all conventional, but you just have to be consistent. And if you work this out, you'll get this is 3.67 meters per second. Okay, question 6. So here's another one with a slope, a plane, inclined. So let's draw that. And it's inclined to this angle alpha. And you've got A at the top, B halfway down, and C at the end. And they're telling us that between B and C, the ground is rough. Between A and B, it's smooth. And we have some block, some object sitting on there with it's going to feel some weight. And remember about resolving. Remember about resolving weights along a plane. This is you sort of resolve it into a triangle, and then you know that this angle is also alpha. So I'll put that in purple just to make sure you know it's the same thing. This angle would also be alpha. Okay, we're about ready. So they want the acceleration that the thing is feeling when moving from A to B. So from A to B, then what is the net force? Remember that F equals ma. So what is the net force felt from A to B? Well, it's a smooth surface, right? So the only force it's feeling is the force of gravity. And we're looking for the motion along the plane. So we're looking to resolve it. So we're looking for this component of the weight. The other component of the weight is acting into the plane, and that's being kind of counteracted by the reaction force from the plane. So that thing kind of cancels out. So the only component we care about is the one along, which of course is the one that's going to be moving it along, accelerating it along the plane. And that's just mg sine of alpha. And this is equal to ma1. And if you solve, you get that a1 is equal to 2.8 meters per second. The mass cancels. Okay, well that's all well and good. Now what about from B to C? Well, now you've got a rough plane. You got your thing sitting on it. You've still got the weight acting down, but now you've got this, and the reaction force acting like that, combating that. But now you've got this friction force. So the force of friction, as usual, is mu r. And so this is going to be mu times the force that the block is exerting, is pushing on the ramp with. So that's the other component of the weight. So that's mu, and this is mg cosine alpha. So that means that the net force is, again, the force going that way down the ramp, the one from the weight of the block, which is mg sine of alpha, minus the force of friction, which is mu mg cosine alpha. And this is equal to ma2. So, notice again that the masses cancel. And if you solve this, we have all the bits that we need. We get that a2 is equal to minus 2 meters per second. So once it gets to the rough part, it's actually being accelerated in the other direction, by which I mean, it doesn't mean it starts moving in the other direction, because that would be weird, because the friction force would go down, but it's slowing down, which makes sense, right? It's moving at some speed, and then it enters the rough region, starts feeling a friction force that it wasn't feeling before, and so it starts experiencing this negative acceleration, also known as deceleration. So now they want the distance AB. So I'm going to use that equation we had before, that V final squared is equal to V initial squared plus 2AS. And so I have that, should I copy this? Let me copy this diagram so we can have a look. Blah, blah. There we go. So first I'm going to look at the motion from A to B. So the velocity at, the velocity at B squared is the initial velocity, which is 0 because it starts from rest, times 2 times A1, the acceleration that it feels during this period, times the distance AB. And then I'm going to think about the velocity at C. We're not done yet. The velocity at C squared is going to be the velocity at B squared plus 2A2 times BC. All right, just applying this equation twice. So if I plug this equation into that one, I get that this is 2A1 times AB plus 2A2 times BC. And I also know that BC, we're told that the whole thing from A to C is 5 meters, so BC must be 5 minus AB. So this is 2A1 times AB plus 2 times 5 minus AB, A2. And this is equal to VC squared. And we're told up here that VC, the velocity at C, is 2 meters per second. So VC squared is 4. This whole thing is equal to 4. And this is equal to 5.6 AB minus 20 plus 4 AB. And you can just solve this for AB being equal to 2.5 meters. So now they want us to talk about the time taken. So we know that because it starts from rest, that means that at B, the velocity is going to be equal to A1 times the time taken to get from A to B. Great. And the velocity at C is going to be equal to the velocity at B plus A2 times the time. So this was the time from A to B. And here it's going to feel the acceleration from B to C. So this is equal to, and I plug in VB, A1 times the time from A to B, plus A2 times the time from B to C. And this is going to be equal to, A1 is 2.8, T, I'm just going to write this as TB, same thing, minus 2 times the total time minus TB. So TB to C is the total time minus the time it took to get from A to B. And so this is 4.8 TB minus 2T. And we know the velocity at C again, we know that it's equal to 2. So now we have something in terms, we're solving for T, right? But we have this unknown TB, so we need another equation. And we know that distance traveled, AB, must be equal to initial velocity times time, which is initial velocity is 0, plus 1/2 acceleration times time squared. So and we know that AB, we've solved for that already, and so this gives us that TB is equal to 1.336 seconds. And therefore we can solve this, that T is equal to 2.21 seconds. And there we go. Okay, final question, question 7. We have a velocity time graph here. So, I mean, the important things to remember with these kind of graphs is always that the area under the curve gives you the distance, and the derivative or the gradient of the curve gives you acceleration. So acceleration is, you move up, you differentiate once, and to go the other way, you integrate. So, we want the value of V. So we're given this differential equation for the remaining 12 seconds. So that's the equation of this curve, right? But before that, it's just a straight line. So now they want the value of V when T is equal to 3. So at this point, after it's had the straight line. And the magnitude of the acceleration for the first 3 seconds. So we're just looking at the straight line motion. If you think about differentiating this, the derivative of a straight line, the gradient of a straight line is a constant. That's what defines a straight line. Same gradient everywhere. And so it means the acceleration is a constant. Whereas in this curve, the acceleration is changing. So find the value of V when T equals 3. Well, we know that this thing must be continuous. So we have that V of 3 is minus 4.8 seconds, because this thing is only valid from 3 seconds onwards, but it's still valid at T equals 3 seconds. So we can just plug in the T there, T equals 3, and get the value for the velocity. And we know the acceleration from 0 to 3, well, that's just going to be the velocity divided by the time, the change in velocity divided by the change in time. And this, I'm using big deltas instead of derivatives here because it's a straight line, so it's the V and T are, you don't have to worry about the acceleration is constant the whole way. So you just have to look at like the total change in both of these. And so that's going to be minus 4.8 over 3, which is minus 1.6. So that makes sense, right? The velocity is decreasing. It's becoming more and more negative. So, sorry, not decreasing, sort of technically decreasing in the sense that it's becoming more negative. The absolute value of the velocity is increasing, as in you're getting faster, but you're heading backwards. So that sort of counts as decreasing in a weird way. And that's reflected by the fact that it's a negative acceleration. The acceleration doesn't know if you're slowing down or sort of accelerating in the opposite direction. Those are both equivalent. So the second question is to find the maximum velocity of p whilst moving from b to c. Well, we know how to find the maximum, right? We just differentiate. So dv dt, if we look back up at our differential equation, you'll see that this is equal to minus 0.4 t plus 4. And this is equal to 0 when t is equal to 10 seconds. So the derivative is equal to 0 at the maximum or minimum at the turning points. And you can see quite just by even looking that this thing is equal to 0 when t is equal to 10 seconds. So what is the velocity at 10 seconds? Well, you just plug it in to the original equation and you get 5 meters a second. Okay, now they want the average speed of p. So firstly, we're moving from A to B. So average speed is, change in position divided by change in time. And so let's first look at while moving from A to B. So the distance traveled from between 0 and 3 seconds, which is A to B. Sorry, if you look at, A and B, here's A, and this is B here. So I'm actually just looking at this first initial period with the straight line from 0 to 3 seconds. So from 0 to 3 seconds, well, it's just constant acceleration, right? So we can use the constant acceleration equations. And the time is equal to 3 seconds. We know that. We know the acceleration that we worked out before. And so this is equal to 7.2 meters. Now, what is the distance as it goes from 3 to 5 seconds, which is the other section from A to B? Well, for this, the motion is a little more complicated. It's all curvy, so we have to integrate instead. So we're going to integrate the expression for the velocity over time from 3 to 5 seconds. And this is equal to minus 0.2 on 3 t cubed plus 2 t squared minus 15t, evaluated between 3 and 5. And if you just plug this all in, you get that this is 4.53 recurring meters. Okay, so now they want us to, you might want to add those two up to some total. Right, sorry, you would add them up to some total, and then you would get that the V average, which is this total divided by 5 seconds, gives you 2.35 meters per second. Okay, now they want us to do the whole journey. So we have this section already done from A to B, but now we just want to do from B to C. And that's, again, we just integrate V of t dt from 5 to 15, I think. Yeah, 5 to 15. And this is exactly the same procedure as before. You'll get some amount, then you'll have some total, S divided by 15 seconds. And this is your V average for the whole journey. And so this is equal to 3 meters per second. And there we go. That's all done. I hope that was clear. Please let me know in the forums if you have any questions about this paper, and I will see you next time. Bye.